And conventionally, making a clock, we use what we call the double resonance approach. That means when we do the optical pumping and then we shine, okay, this is the case for microwave clock. Okay, we talk about microwave clock, optical clock. They are very similar. We always have to do state preparation. It's just the transition frequency between the two clock states is different. The microwave clock, this is in the microwave frequency range. Optical clock, this is the optical frequency. But when we do the optical pumping, and then we can probe the clock transition, in this case, assuming there's a microwave, we shine the microwave, we can bring some propagation back to the other state, and this pump light can also serve as a probe. And by scanning the microwave frequency, we'll find the resonance. And this clock resonance is how we're going to measure time, because we can lock a local oscillator to the clock resonance. So any oscillator can be stabilized or disciplined by this stable atomic resonance, and that's how we make the atomic clock. This clock approach is what we call the passive approach, meaning like we have to engage a probe to determine where the transition frequency is, and then use that to correct another oscillator to maintain a stable oscillation using atomic resonance as a reference. So one approach is what we call the double resonance, means we need optical resonance and a micro resonance, or even two optical resonance, to make a clock. And for the microwave, we can also do what we call the coherent propagation trapping approach. That doesn't require microwave, but we can use two optical fields. The same principle can be applied for optical clock as well. It's just nobody does that. And this is really based on stimulated Raman transition method. A two coherent optical field that have well-defined phase between each other, it can serve like a microwave excitation between the two ground state sublevels. In this way, we can also see the atomic clock resonance when the optical frequency difference between these two optical fields is equal to the energy splitting between the two clock states. So either way, once we are able to probe the clock resonance, which is stable, insensitive to basically any other physical quantities, then we can use this as a reference signal to stabilize any oscillator to generate a stable oscillation, and that can be used as a clock ticking signal. So this is the passive atomic clock approach, using two different spectroscopy methods, the double resonance scheme or the stimulated Raman transition. Okay, so later I published this paper just really improving the signal to noise ratio by a huge factor for what we call the CPT clock. So the conventional CPT resonance, if we put on the same scale, is something that looks like this. You can see the tiny bump on top of the this blue line, and using what we call this additional pumping scheme, push-pull optical pumping, we can boost up the signal by a huge factor. And this is great because increasing the signal to noise ratio helps with the clock precision or the sensitivity of other sensing application. Let me see. Okay, so usually it's a bit harder to explain, like why this stimulated Raman transition can give us a signal in the energy level diagram. I mean, because that really something you have to do is you have to calculate the transition probability with two coherent optical fields and how they will end up, when it's off resonance and when it's on resonance. And that's the total transmission of the two optical fields to reveal the atomic clock resonance. But another classical picture is actually more straightforward. So what it does, if you look at the clock state and try to find out a classical observable for that, the atomic clock, microwave atomic clock, especially for example like cesium, we still use cesium to define time, even though it doesn't offer the best accuracy and the precision currently. But use that as an example. If we choose a clock state, that means the angular momentum projection is 0, and it's insensitive to the magnetic field. Not totally insensitive. It has a second order sensitivity, but it doesn't have first order sensitivity. When we look at a classical observable, like a spin, this is actually the electron spin. We find once we generate a clock superposition state or the coherence, and then we measure the electron spin, it's actually oscillating along the z direction, and z is defined by the magnetic field. And this oscillation frequency is equal to the clock frequency. The push-pull optical pumping is actually using the photon spin to drag the electron spin and synchronize that in the same way. So if we imagine we are sending the light pulse, so what happens is this stimulated Raman transition, if you look at it in time domain, is equal to the light pulses in time, but alternating the spin, the photon spin direction. We use this alternating photon spin to maintain the oscillation of the electron spin at the same rate. So as long as this photon spin pulses is commensurate with the clock transition frequency, we see the maximum amplitude of the electron spin oscillation. And this is how we do what we call the push-pull optical pumping. It maximizes the clock state coherence or the superposition state amplitude and boosts up the signal by a huge degree. And with that, we are able to see a much better performance because of the large SNR without sacrificing the line width. And then just a little bit more about the optical waveform of the push-pull optical pumping. We talk about the vapor cell require buffer gas. When we add buffer gas, the optical transition line width is no longer the same as the natural line width because the collision between the atom and the buffer gas particles actually broaden the optical transition line width. When it gets broader and broader, we actually figure out we can still maintain this high efficient optical pumping into the clock state by optimizing the waveform of the push-pull optical pumping. So it will concentrate the population into the clock state regardless how broad the optical transition is. And this is just about that approach. So so far I've been talking about the passive clock. So a quick summary of a passive atomic clock is we need atomic species as a reference, which provide a very stable internal atomic transition. And we probe that transition and use that to correct the local oscillator frequency to discipline this. And in this way, this closed loop allows to generate a very stable clock ticking signal. And there are two possible ways, as I mentioned. One, we can do what we call the double resonance approach. We have optical pumping by the laser, and we shine the microwave, and then to interrogate the center of the atomic clock resonance. Or we don't need a microwave. We just modulate the laser to generate optical sidebands. They are naturally phase locked, because it's from the same carrier, and can also excite the clock resonance and correct the local oscillator to generate stable signal output. And this is the passive one. The passive one means we need an external feedback loop, a closed loop. Use atoms as the time reference and to stabilize a local oscillator to generate a clock signal. But there's another approach we call the active clock. Active clock does not require a feedback loop. They use atomic or molecular species to directly generate oscillation signal from their internal stable transition between their internal quantum states. For example, hydrogen maser, rubidium maser, ammonium maser. And maser is similar to laser, just in the microwave region, but it's not the optical region. Usually people do the state prep using, for example, magnetic field to spatially select the state of the atom or the molecule, and then or doing optical pumping to do the state preparation. and put those atomic or molecular species inside a microwave resonator, and then like a laser, it will generate a coherent microwave output at a stable frequency. And this is what we call the active clock. This approach does not require a feedback loop, which the reason I keep talking about the feedback loop is because when later people think about, try to make a miniaturized atomic clock, this is actually the major burden of making a small portable or field deployable atomic device, because it is power and takes space. If we can get rid of these peripheral components and try to make a very small size active clock, and that will make the size and power consumption way much lower. But unfortunately, so far the Maser approach, they usually occupy lots of space. The reason of that is because the microwave wavelength is way much longer. For hydrogen, it's about 1.4 gigahertz. Rubidium, you can have rubidium-85, which is about 3 gigahertz, or rubidium-87, 6.8. And for ammonia, it's pretty high. It's like 27, 28 gigahertz. But still, if you look at the scale, it's still like several centimeters long, okay? And even like meters long. And then the chamber has to be well designed, which does not react with those atomic or molecular species. Sometimes it can cause the problem. So Maser system actually pretty good. I mean, in fact, if you look at the real timekeeping world, hydrogen Maser is actually the key role maintaining the time in our world right now. The best optical clock, even though I mentioned, 10 to the minus 20, or integrate from 10 to the minus 18 to 10 to the minus 20, is great, but they cannot continuously operate for, it really depends, like from a few days or maybe to a week, something like that, because laser just went out of luck so often. And people will ask, well, how do we keep time, between, like the different rounds of those high precision clock? It's actually hydrogen Maser. This is, the clock system can run forever most of the time. I mean, when I say forever, it's not totally true because it has a finite lifetime. And also for season phantom, usually they turn it up, running for 3 months and stop it, right? So you need to find something to fill up the gap. So really, talking about the fundamental research or basic science research and the real application, that depends on the requirement, right? So for real application space, this is something we want to think about. Okay, so how about the vapor cell? Can we make an active atomic clock with a small form factor and low power consumption? And this is the main topic I want to talk about for this one, this innovative approach. And this is called the laser push-pull laser atomic oscillator. We can actually make a clock without feedback electronics by simply assembling or putting these parts together: a vapor cell, a laser gain medium, and a laser cavity, and some optics. Just adding this together, it will generate the clock signal either in the optical form or the electrical form from the gain medium, using the push-pull optical pumping physics. And that's why, in the previous 3 slides, I was talking about the push-pull optical pumping. Just think about this way. We talk about the clock coherence is equivalent to electron spin oscillation at hyperfine. Sorry, I didn't explain the hyperfine frequency. So hyperfine interaction is the interaction between electron spin and the nuclear spin. And that splitting, we can find a stable pair of the hyperfine sublabel to use that as a clock reference. And that stable pair of the hyperfine state give us this classical observable like an electron spin pointing along the z direction and oscillating at the hyperfine transition frequency. And this is the clock frequency. We can set up something like that. So the light pulse, by the time it arrives at the cell location, it has a photon spin aligned to the electron spin. And then when it comes back, after the single round trip back to the same location, they also align well to each other. So we can kind of imagine this is the condition which gives us the lowest cavity loss of the photon, and therefore this has the highest gain. So naturally, when you put things together, it will just oscillate spontaneously at hyperfine clock frequency. So that's the time domain picture. If you talk about like more like quantum picture, it's like, we originally had lots of spontaneous photons coming out from the gain medium, and some of the photon pairs, they have the optical frequency difference matched to the clock transition frequency. So through the stimulated Raman physics, this pair of the photon will actually get transferred to the coherence of the atomic clock state. And then when those photons travel back, the photon can retrieve this coherence back to the pair of photon again. So it's basically temporarily store the information of the pair of the photon, and then it retrieve back after the round trip. And then only those pair of photons which have the optical frequency difference equal to the clock transition frequency can survive in this round trip inside the laser cavity. And then the pair of photons will get amplified by the gain medium. So eventually those pair of photons will get amplified. And not just that, when we talk about pair of photons, it doesn't mean we only see two optical tones. We actually see like a small comb, optical comb with a teeth spacing equal to the clock frequency. So for example, if we use cesium, this will be around 9.2 gigahertz apart. That's the teeth spacing. So this occurs spontaneously, and using this approach, we can actually make very small atomic clock using the vapor cell without the electronic feedback loop. So the idea was proposed a while ago, and by the time when I tried to prove it, I didn't use cesium because for technical reasons, you have to find the right gain element. So I was actually using potassium. Potassium has a nice feature, which has a hyperfine frequency at 462 megahertz, and the equivalent half wavelength is about 32.5 centimeters. So I can use like just a commercial optics, to put things together to prove that concept. So that's the original experimental approach, and then it's just pretty straightforward. You put things together, and then you can see just generate the pulse at hyperfine frequency. The repetition rate of the pulse is equal to the hyperfine frequency, and you also see that small comb there with the T spacing equals to the potassium 39 hyperfine frequency there, and that's kind of the proof of concept, and quickly measure the stability, and we'll say, oh, this doesn't look very good because that's a reason for that. That's the reason why people didn't use potassium, because the hyperfine splitting is too small. It's only 20 times smaller compared to cesium 133. So 0.46 gigahertz compared to 9.2, right? So it's 20 times smaller. When the hyperfine splitting is smaller, that means its second order magnetic field sensitivity is higher. It's much higher, and therefore it's not good transition for making a clock. But at least this will prove the concept. And it depends on what the hyperfine transition we use. Like we talk about, we can choose internal quantum states to make the sensor for different purposes. If we use a magnetic sensitive hyperfine state, we can make a clock. We use the sensitive one, we can make a magnetometer. So this laser atomic oscillator requires just the laser gain element, and also the vapor cell can make an active clock or a self-oscillating magnetometer, which does not require a passive probe. So depending on which transition we use, we can actually make a different kind of applications. And for magnetometry, it actually demonstrates really, really good sensitivity in the Earth field, because this doesn't require like magnetic shield, and you can actually get down to like 10 femtotesla level using this approach. Okay, so over there, the previous few slides, I've been talking about the physics of push-pull optical pumping and using potassium as a proof of concept experimental demonstration. And after that, what we want to do is we want to switch the atomic species from potassium to cesium, because after all, cesium has a larger hypermass splitting. And again, this is still the atomic species, we use to define time, right? So if we consider, this commercial atomic clock business, in 2011, the first so-called chip-scale atomic clock was, commercialized, but when we say chip scale, it depends on how you define chip scale, right? Because like fish and chips, the chips is actually pretty big, and it can also be real, like a microprocessor chip is really, really small. The CSEC, the chip scale atomic clock, has a volume like 15 cubic centimeter, so it's about the size of a matchbox, and to me that's not truly chip scale. The laser atomic oscillator can actually make a better, in terms of the chip scale size, because we can completely get rid of lots of electronic burdens, local oscillator, microwave synthesizer, clock loop, control electronics, and even consider other approaches. If we don't use vapor cell, you have to trap atoms with laser beams or using electrodes to trap ions. So you can greatly reduce swap, for that aspect. But of course, if you want to consider whether you want a smaller size or better precision, that's kind of the factor of consideration. The vapor cell-based atomic clock, I mentioned before, the best demonstrated result is something like from 10 to the minus 13, integrate down to 10 to the minus 15. If you want to get better than that, then you still have to use some other existing technology for better clock stability. But if 10 to the minus 13 is good enough, then vapor cell can definitely do that. So for laser atomic oscillator, if we switch from potassium to cesium, naturally the frequency will jump from 0.46 gigahertz to 9.2 gigahertz. And the size of the cesium-based laser atomic oscillator can be really, really small, like smaller than 0.1 cubic centimeter. And the reason of that is because now we know the cavity length, which is about the half of the microwave wavelength, can be just like about a centimeter. So you can actually add all this part together, the cavity mirror, the wave plates, the vapor cell, and the gain element. And if you really compare the physical size, this is what the size of the CSEC looks like, the commercialized. And the laser atomic oscillator is actually only like this big. So switching from potassium to cesium actually gives a lot of advantage. And this is really the very new kind of a clock, vapor cell clock approach. It's not passive, it's active, and also it gives us a great opportunity to make super small atomic clock. So fortunately, we were able to start working on the cesium laser atomic oscillator. And initially, of course, I didn't start with a super small scale because, it's nice to use commercial optics and your finger is like, my finger is big, right? Like sausage. And it's hard to work with a super small optics. So I still use commercial optics, and instead of using the first order cavity, I use seventh order, means like the cavity length is like 7 times longer than the half wavelength of 9.2 gigahertz. But this is with cesium. And again, very simple, just a bandwidth optics. This is a Bragg reflector, 2 quarter wave plates, a cesium vapor cell, a gain element, confirmation lens, and then you add them together, and you see the oscillation at 9.2 gigahertz. And you also, if you look at the optical spectrum, you also see this small span optical comb with a T spacing equal to 9.2 gigahertz as well. So that's what we got, and the next step is we try to make a better gain chip, which allow to shrink the size down, which I don't personally think I have the skill for that, but somebody at Sandia is very good at this, just making a very small devices. So that's what we're going to, try to demonstrate. And again, just to show, yes?
So go back a slide.
Uh-huh.
So now how big is that?
This one?
Yeah.
This is about 11 centimeters because it's 7th order.
11 centimeters?
Yes.
Okay.
Yeah. But this is active. Yeah. So like I said, so what I really need to do, I just need to connect the electrical power to the laser gain chip, and then automatically generate the oscillation at 9.2.
How about power? You use laser, right? How about power consumption? Is it high?
The power consumption, no. So the power consumption on gain chip is about 40 milliwatts. Yeah. All right. Okay. So I mentioned, depending on what quantum state we use, we can use the clock state. It's normally called 0, 0 because the nth quantum number is equal to 0. It doesn't have first order sensitivity to magnetic field, but we can also use different transition to show we see all different oscillation signal due to different hyperparameter transition for season. And if you zoom in, you can actually see the 6 hertz modulation on that. And when you look at the noise floor and the oscillation depth, we can achieve like 10 to 100 femtosecond per square root hertz sensitivity in the Earth field. And this is also active magnetometer because it doesn't require electronics. Just some results, like as an example. The oscillation has its own frequency derivative depending on how stable, because one thing I didn't mention is this approach is also affected by a mechanism called cavity pooling, which is the same mechanism you will see from a massive system. Any cavity-assisted system, if you change the cavity dimension, it will cause the cavity pooling effect. So atomic species dominates the oscillation frequency. But the cavity, if you change the length, it still pulls the oscillation frequency a little bit. And that pulling factor is about 10 to the minus 4. So for example, if we want to achieve 10 to the minus 12 stability, we want the cavity stability to be 10 to the minus 8 because of the 10 to the minus 4 factor there. But here, just to show you how we further improve that. So at the very beginning, when you just put things together, you can easily get oscillation. But if you look at the RF spectrum, you see it's drifting around. But once you just tweak it a little bit, you can make it more stable. And this is about the frequency stability. But also for microwave or RF oscillator, people cares about the phase noise a lot as well. And the phase noise is basically the line width. Can be characterized by one side of the RF peak, in the RF spectrum analyzer. The line width is proportional to the phase noise close to the lower frequency. And you can see this is a log scale, so it's not the real linear scale line width. So the actual line width should be just around, if we talk about the 3 dB line width, it's very near the peak of the oscillation signal. And after the improvement, you can see the line width gets much narrower, from here to here. So it just requires some detailed tuning and tweaking, and we can make a very stable output. But again, this is all based on the benchtop setup. To make a super small one, that's something we have to work on because they require really fine tuning capability. And this is kind of goal, eventually just make something like that. You have a nadir-bonding vapor cell, or called the MEMS cell, and then you have the gain chip, the calibration lens, the weight plate, and the optical bandwidth limiting component. So this is about one type of a vapor cell, innovative, atomic device. Next one, I'm going to talk about the magnetometry. Okay. Do I have any questions so far? No? All right. Okay. Magnetometer. Peter Swain will talk more about this because he has been working on magnetometry a lot. I used to work on this for a while, but now I focus more on the electrometry, electric field sensing. But this is part of my work as well. The major thing I want to point out is, well, first of all, I don't want to go into detail with this. I think Peter will talk about this, how we generate the signal and use the magnetic sensitive states to detect the magnetic field. But in general, to do the measurement, usually we want to convert the resonance signal into this kind of dispersive-like signal. So you have this zero crossing thing, so you can easily detect the shift of the resonance by measuring the shift of the zero crossing. It's very similar to interferometry. You want to see the fringes and want to use the zero crossing part of the fringes to determine the shift of the frequency or the phase. And this is kind of the quick overview. Say, okay, how we use alkaline metal atoms, and this is the kind of the equation of motion of the hyperfine spin. It's characterized by T2 time, T1 time. So T2 is the decoherence time, T1 is the spin realization time, and the gyromagnetic ratio, magnetic field, this big F, that stands for the hyperfine spin. So there's a combination of electron spin and the nuclear spin. And you can use just work through the math. You can find the steady state solution and determine the size of each spin component, and they can be probed independently, depends on which one we are interested in, and use that to measure the magnetic field. The fundamental uncertainty of the magnetic field sensing has something to do with the gyromagnetic ratio, right? So larger ratio means it's more sensitive to magnetic field. The same amount of magnetic field or the same strength of magnetic field give you larger Raman frequency or the precision frequency. This N stands for the number of atoms and the volume, this is density, sorry. The atom density and the volume, and T2 and the interrogation time tau. Anyway, this was demonstrated first time at Princeton by Michael Roman's group, showing this surf region magnetometry and demonstrate the first time you can get femtotesla level sensitivity. And I want to talk about the physics a little bit. The reason the surf, what they call surf, spin exchange realization free, is because the decoherence normally is dominated by the spin exchange effect, which I kind of talk about in part one. When two atoms collide with each other, they exchange the spin. And this causes a random flip of spin between the two frequencies. When you get ensemble average, you will see it causes the decay of the oscillation, right? But this can actually be mitigated if the spin exchange rate is way faster than the difference of Raman frequency between the upper and the lower hyperfine manifold. And that's what they call the spin exchange realization free regime. And that requires really, really low magnetic field environment. So this magnetometer approach has to do inside, most of the time, inside the magnetic shielded space. So to enable the spin exchange rate to be faster than the than the Raman frequency. And anyway, it was demonstrated and it worked, and we can achieve like very high sensitivity. So it was first time published in Nature, long time ago. I don't remember which year, like 2003, yeah. And then they also show, well, actually, yeah, we can demonstrate like femtotesla, but if we do the gradiometry, so gradiometry means you have like, for example, two magnetic field sensors, right? And then they are not at the same location, and we measure the signal difference between the two. So we only measure the field gradient, but not the total value. And that gives us even better sensitivity, but depends on what the baseline is. So usually the gradiometry, you have the unit like per centimeter, per millimeter, or something like that. But gradiometry approach is actually good because for the scenario, like if you want to detect the magnetic field source, which is close to you, and we know usually the magnetic field sources, they are, that's classically, there's no magnetic monopole. So it had to be at least dipole. And dipole decays like 1/r³. So you can always find a large gradient signal if the source is close to you. If the magnetic field background comes from far distance, and then you can use the gradiometry approach to delete or remove that common noise, common magnetic field background. So in this paper, they also talk about their gradiometry, which was able to demonstrate like 0.2 femtosecond. All right, so the major innovation I want to talk about here is making a magnetic gradiometry without using the electronic subtraction. In the past, what they did is they have either different cells or single cells with multiple detectors. And they do electric signal subtraction to remove the common magnetic signal, right? And that requires electronic processing, right? So you subtract the electrons. I mean, we already convert the magnetic field signal to the electric signal, and then we do the subtraction. The downside of that is apparently, if your electron has a noise, and they have independent noise, you cannot subtract each other, because you won't be able to remove those independent noise. If we can do this kind of subtraction without going through the electronics, that'll be great, because then we don't need to be worried about additional noise coming out from the electronics. So this is the kind of innovative approach. We make magnetic gradiometer without electronic subtraction. The idea is to shine the laser beam and then use two vapor cells in a line, and then we excite, let me put it this way. We actually excite the atomic coherence between the Zeeman sublevel. So it's also the hyperfast sublevel, but it has a magnetic field sensitivity. When we do that, it actually, through the stimulated Raman scattering, it generates optical sideband. And the spacing between the carrier, which is the incoming light, and the scatter sideband, from the atom inside the vapor cell, is equal to the transition frequency of the two magnetic sensitive sublevels. And when you pass through the second cell, it will also generate another sideband. If these two see the same magnetic field strength, the spacing between the sideband and the carrier will be the same, and then F1 and F2 will be equal. And so we will see nothing. But if F1 is different from F2, we will see the B node. And that B node directly gives us the magnetic field gradient. So the idea was there, and then we actually did the experiment and verified that, and it worked. And the theoretical work is actually based on my early modeling work, like in 2007. It turns out this can be useful, just for this. You never know, like, what you did before can turn out be useful. Okay, so we did the modeling just to see, okay, once we engage the laser beam, CW beam through the vapor cell, and that vapor cell already has atomic coherence, which is sensitive to the magnetic field, how the sideband will generate as a function of propagation distance. And then use this modeling, we actually can measure the data and match pretty well. The sideband strengths at different optical frequency and the function of distance. And so that's what we did. We have the two vapor cells, and then we try to probe their signal. This one is the probe, and this one is the pump. So the pump is actually generate the atomic coherence, which is sensitive to the magnetic field, and the probe just to see the time evolution of the coherence due to the optical sideband. And then this is actually the B node of the optical sideband, and this is proportional to the magnetic field gradient. And this can be really small form factor, because then we also don't need additional electronics to make a gradiometer. All right. Okay, a magnetic field gradiometer has lots of application, like I mentioned. If the source is at a short distance, from a short distance, we can get a good signal with a good rejection of magnetic field background. One important application is MCG, magnetocardiography. And I don't want to pronounce this word. So MEG, that's for measuring the brain signal. So we have the commercial system. People make the MEG system using SQUID, magnetometers, the superconducting, quantum interference device. but that require cryostate, like 4 Kelvin helium, liquid helium coolant, to make those squid divided to work. The nice thing about the vapor cell-based magnetometer, we don't need to cool down our sensor. We actually have to heat up a little bit, to get enough vapor density there. And then we can make a very dense array, or like a wheelable. You can put the sensor array on your skull, regardless what the shape of your skull is. And this is actually a very useful application. This animation, just like the example I made before, we use our sensor array and measure the signal. We can localize where the source is from your brain, from the cortex. And using that magnetometer with a gradiometry capability, you can reject the magnetic field background. This work was still down inside a magnetic shield, but magnetic gradiometer in principle can work just as well as this in the Earth field environment. Once you have this capability, you can do lots of things. I think one useful application I'm super interested is the human brain interface. Instead of doing this invasive, thing, to put the electrode inside your brain, nobody wants that. You can use this just outside your skull and still read the brain neuron activity. Anyway, tomorrow, Peter Swin, we'll talk more about this. All right. Okay, so this is the final thing, final example I want to talk about. And this is about the electrometry, measuring electric field. Okay, so we talk about different vapor cell-based applications. Electric field is the kind we actually don't take advantage of the ground state quantum states or sublevels. We actually take advantage of the highly excited rebirth states because they have very large electric dipole moment. So in the classical picture, you can kind of see, well, electron is kind of orbiting around the core, of the atom, and core has positive charge, electron has negative charge. Of course, we know this is just a classical picture, right? In real world, the quantum picture, electron is not orbiting around it, it's a cloud, right? But still, you can see as long as the separation between the positive charge and negative charge is getting larger and larger, we can get the higher or larger electric dipole moment. So when we excite the atom to the rebirth state, we will see a large dipole moment. If we really look at the radial wave function, so these are the calculated radial wave function for principal quantum number equal to 100, and you will see the electron cloud actually extended up to 1 micron, and this is a pretty big atom, right? Compared to the ground state atom, it usually is on the order of a few angstroms, and this is like 10,000 times bigger. This large size atom has a large electric dipole moment. When electric field is interacting with that electric dipole moment, it causes the energy shifts on those rebirth states. And by measuring that shift, we can determine the electric field strength. So that's a typical approach for atomic rebirth electrometry. Just quickly go through this. This is a well-established thing. We know for hydrogen, you can calculate this pretty well, even consider relativistic effect or any other additional energy level shift mechanisms. But roughly, you can calculate each energy state using this rebirth formula for hydrogen atom. For non-hydrogen atom, for example, hydrogen-like atom, like alkyl metal atoms, we usually introduce this quantum defect parameters, and this is kind of the first order approximation, and you can have a high order formalism like this, which can allow you to calculate the value of those rebirth states pretty precisely. But by the way, this is the empirical approach, meaning you have to experimentally determine those parameters. You cannot just calculate it. Well, you can calculate it, but unfortunately, we don't have computer power to do even this atom simple like this, right? So that's why people talk about quantum computer. Okay. The Reaper electrometry. I want to talk about the most common approach or the mainstream in this research community. People have been focusing on using Reaper state for measuring electric field at high frequency. When I say high frequency, like from hundreds of megahertz to hundreds of gigahertz, even up to terahertz as well. So what we do is we actually look at, so this is kind of zoom in energy level of the Reaper state near n, principal quantum number n equals to 100. And for s orbital, p and d and f and so on. And you can kind of see the transition frequency here is on the low order of like a few gigahertz there. And you can choose different sets of Reaper state. The original approach of Reaper electrometry is if you probe a specific Reaper state, like for example, s equal to 100, and then you shine the electric field with a frequency, oscillation frequency that matches to the transition frequency from this state to the nearby state. It has to be anti-parity, right? So we know the selection rule, you cannot do from S to S, it has to be from S to P. And so it can be this from this 100S to 99P or 100S to 100P. And if it's close to the resonance, we will see this, what people usually call the orthoton splitting. It's really just like the Rabi oscillation between these two levels introduces additional dress state, with a splitting, which is proportional to the Rabi frequency. And if you look at this simple formula, this Rabi frequency is only determined by the electric dipole moment and the electric field and the Planck constant, right? And electric dipole moment in principle is also defined by the fundamental constants. But of course, for atom like this, you have to measure it to determine it. But anyway, in principle, if we know the splitting in the unit of frequency, we can calculate electric field trends directly. So this is like a direct measurement, can be a calibration-free electric field measuring device, can be a traceable standard. But the sensitivity is not that great because measuring the splitting, you have to determine the splitting depending on, precisely enough, that depends on the line width, of the two dress states. And you also, that's a very narrow bandwidth because this approach requires the detection frequency to match the transition frequency between the pair of the Reaper, between the two Reaper states. So anyway, but that's the original proposal. So later, to improve the sensitivity, we actually use what we call the heterodyne method. I'll talk about that in the following slide. But anyway, first of all, I want to talk about is my focus is actually not measuring the RF electric field or the microwave. I've been focusing on the very low frequency, let's say below like kilohertz. And the reason of that is, well, there are a few reasons. So, well, first of all, I want to point out, no matter how people claim their Reaper RF receiver, how great it is, but if you actually compare with the classical, conventional technology, for example, the GPS receiver or your cell phone, their sensitivity is way better than any RF Reaper electrometer. It's not surprising because even electronics is based on quantum physics. And the nice thing about the high frequency is you don't need antenna. So one thing we do know, detecting electromagnetic signal, if you want to have a good sensitivity, you want your antenna to be about the same size as the wavelength. And low frequency is just very hard to do. But high frequency, you can easily make a small antenna with a good impedance matching, and then you can make a very good receiver, especially now those RF front-end electronics, they have very low noise. So it turns out when you compare the sensitivity with the conventional electronics and the Reaper receiver, the conventional electronics is just still much better. And the second bullet is just simply just I talk about, the antenna length, the dimension of antenna has to match the wavelengths. So high frequency for the conventional electronics is not a big deal. But if we say we want to detect the low frequency, similarly, magnetometer, if you compare atomic magnetometer with a pickup coil for magnetic field, we can easily see you can make a nice magnetometer for frequency above megahertz, just simply using a few turns of a copper wire, compared to atomic magnetometer. And for a similar reason, if you want to detect high frequency, usually the dimension can be much smaller. And also for electronics, usually what they suffer is the 1/f noise. So the low frequency become harder and more difficult for them to detect. So anyway, overall, for atomic sensing, as I pointed out in part 1 of my talk, usually they are good, they are better for low frequency band, low data rate, for example, clock, extremely low frequency. For electric field and magnetic field sensing, we only see advantage so far if the frequency is low enough. If the frequency is, say, above 100 kilohertz, the conventional technology is way better. Okay, so this is a quick comparison chart. To make a fair comparison, you have to say, compare with about the same form factor of the sensor side. So for example, if I use a vapor cell with 1 centimeter long path length for the laser beam compared to 1 centimeter long antenna, the low frequency detection is way better than the conventional electronic approach. For the high frequency, those purple dots, they are the number you can find from the literature. So far, the best is up here, but these two, stars points, they are for your cell phone and the GPS receiver. And this yellow line is the 300 Kelvin black body background. They're still not great. It's about the order of magnitude worse compared to the daily use of electronic technology. And that's why, I've been focusing on the low frequency side, because it does demonstrate and deliver better sensitivity compared to the conventional technology. Okay, and this is just a comparison table. For the low frequency, I call it quasi-DC, electric field sensing. Reber approach, it gives us pretty good dynamic range, good sensitivity, good small form factor, and there's several others, like existing technology. For example, people used to use electric field mill. It's kind of like a turning blade, and then use that to detect the electric field, but it has a large volume. You can actually achieve very nice sensitivity. For example, the cell I've been using, for small size, like cubic centimeter, demonstrate like 100 microvolt per meter. But you can definitely see, people demonstrate 1 microvolt per meter, but with like a few meter long antenna, right? So it depends on what kind of application target you would like to have. If you just want to detect a signal, okay, you can make a very big coil to detect magnetic field with like atto Tesla level, but the coil size is probably like the size of this room. But what you trade is the spatial resolution. If you do care about the spatial resolution, making a large coil or large antenna does not help with that. So if you want good spatial resolution and good sensitivity, the vapor cell-based electrometer will give us the best result. All right, then for the low frequency detection, what are we going to do with that? This is another example. So this is actually the calculated energy levels. There's actually many of those, if you actually go to the high principal quantum number. And because you have so many other orbitals, nearby. But anyway, my point is, if you look at the energy as a function of those Reber states, as a function of electric field strength, you will see it's actually a quadratic dependence, right? And that means, if we try to measure the electric field close to 0, it's very insensitive because it's second order dependence. So in order to introduce good sensitivity, we actually want to add a bias field so we can pick up the linear slope there. So if you have a field fluctuation here compared to field fluctuation here, right? This is 0 slope, give you no response, but here we have the first order response. And this approach is actually the so-called the heterodyne approach. So actually back in 2018 or 2019, I gave a talk in Army Research Lab. They've been working on their Reaper sensor for RF. And they say, oh, wow, we can actually do this heterodyne, even also not just for the DC and also for the RF. And later they actually published a paper talking about making a super broad Reaper sensor, from DC to hundreds of gigahertz by introducing a local oscillator. It's more like a radio tuner. You can introduce a local field, either DC or RF, and then bit with the signal we want to detect and use the linear slope to increase the sensitivity. All right, so in order to show, we can do the low frequency electric field detection, this is kind of the very first experimental setup. We have the conventional laser sources, and we use 2 photons to excite the atom from the ground state to the Reaper state. And we put the cell there. Initially, we want to do some calibration, so we also have the electrodes implemented inside the vapor cell. So we have well-known electric field strengths. Let me see. Okay, and this is kind of the real, setup at the very beginning. Now it's way different. So this is the first tabletop. You can see the blue color light that's from the 480 nanometer. Just good for picture. Blue looks nicer. And then we just want to make sure we do have a good understanding of the energy level shift as a function of electric field for different Reaper states. The curves are the calculated values, and the points, the dots, they are actually the experimental data, and they match pretty well, also including the strengths of the signal. Okay, so the way we measure the electric field is similar to, like magnetometer. First of all, we have to make sure we can see the resonance, right? So this is the Reaper resonance, and the resonance frequency is a function of the electric field. Then, and usually to convert a Lorentzian shape to a dispersive shape is, you just do some modulation and demodulation, right? So you modulate this, and then you do the demodulation, and this 0 slope point will become like a 0 crossing there. And when we apply the electric field, this dispersive curve will get shifted left or right depending on the electric field strength, and then it will convert the frequency shift into the vertical response, and that's the signal of the electric field we want to detect. Okay, the main issue of making the vapor cell-based low frequency electrometer is the electric field screening effect. Okay, originally people, didn't think much about this because, for RF, this is actually not a problem. But for quasi-DC, it's actually the problem, and the reason it's a problem is because we've been using the kind of atomic species, which is actually metal, alkaline metal. So inside the vapor cell, even though the vapor density is low, but it always forms a very thin film, conductive film on the inner surface of the vapor cell. So even the glass cell is not conductive, it's insulated. But because of the existence of this very thin film, the conductive film, the low frequency electric field cannot get into the cell very easily. And you can kind of see why the high frequency can easily get into that. This is different from the skin depth. Skin depth is the other way. This is like for the enclosed conductive surface, and it has a finite conductivity, not infinite conductivity. When you apply external field, it takes time for the free charges on the surface to get redistributed to reach the equal potential condition, right? And that time scale is how fast it can counteract the external electric field. So high frequency can easily get into the vapor cell because charge cannot move that fast. But for low frequency, they can quickly reach to the new equilibrium distribution, and then the internal space will get shielded. So this is actually the major issue at the beginning when we try to do the low frequency electric field detection. And the conventional cell actually is pretty bad because it has something to do with how much atoms can get stuck on the surface. It has something to do with the absorption energy of that atom. But anyway, you can do the modeling, for specific geometry. Actually, there's an analytical solution for a spherical cell, and you know how this surface sheet resistance affect this screening time. And of course, you want this surface resistivity to be as high as possible. But unfortunately, the regular cell doesn't do that. So it ended up, the solution is to choose right vapor cell material, which is instead of a regular glass, if we use sapphire, it actually works way much better. Sapphire cell has very low, not very low, at least much lower surface absorption energy compared to the regular glass cell. So it turns out when we actually measure the electric field screening effect, comparing the sapphire and the regular vapor cell, this is like 1,000 times better. And the way we do that is just applying the electric field externally, like a square wave form. And then we look at the decay, right? So every time you switch the polarity, it will get the signal in, but the surface free charges will try to equilibrate to reach the equal potential condition again, so it will decay. And this decay time constant is the electric field screening time constant. And using a sapphire cell, we find this decay rate is at least 1,000 times slower compared to the regular glass material. Okay, so after that, we're able to achieve, depending on the laser power. So the reason this electric field screening effect has something to do with the laser power, because we do also know there's a photoelectric effect there. The amount of surface free charges has something to do with how much laser power you shine on that, and also the photon energy. Unfortunately, with a 2-photon excitation, 1 photon is way more energetic compared to the work function of the surface, so it can easily excite photoelectrons. But then we can still try to figure out what the surface resistivity or the electric field screening rate or time constant is at basically 0 laser power. You can do extrapolation back to 0 laser power, and you can see we can get almost second long time constant that allows to detect a low frequency. Okay, so we put these things together, and then we kind of measure the same, very similar to magnetometry. Look at the noise floor with different laser power, and you can easily see the ambient 60 hertz AC signal. This is due to the electric field, not the magnetic field. Magnetic field is way stronger than this, and so that's good. So the goal is really to see, we can see the charge signature, and these are the few screenshots, to show, okay, we can see the charge capacitor. If we discharge the capacitor, we don't see the signal again. We can see the charge from a plastic ruler, if we generate statics on that. And anyway, the next one is actually the video, so I hope we can play. Let's see. Okay. Okay, so that's the signal, from the setup, right? Now currently, this is the vapor cell is inside this enclosure, all right? And the capacitor right here, it has a charge, so it's something like 500 volts. And you can see if I just move it. Okay, one thing I do want to point out, although I say quasi-DC, it cannot detect real DC, because as long as there's finite surface conductivity, we will never be able to see a true DC signal. Okay, after discharging it, there's nothing there. All right, the next one is really say, okay, we have some unknown device there, but we know there's a capacitor in there. Okay, and at the beginning, this electron has no charge. we got nothing there, right? But that device has a DC-DC converter, right? So it can charge up the capacitor at a high voltage. Okay, so once you finish charge, you see the current drops to zero, near the zero. So we know it has a charge capacitor in there. And you can see the signal, okay? And this is really low frequency because you can see this is something like a few hertz kind of frequency. And then the last one is the plastic lure. Okay, look at the scope. You see that? All right. So that's the first time, this is a while ago. Actually, it's back in 2020. We show, okay, vapor cell or atoms can actually see, very sensitively see the electric field. And this is the sapphire cell right there. All right. Okay, I think that's it. Let's see if I can go to next. Okay. Okay. Yeah, talking about the prospect. In fact, the reason I think this talk's been focusing on more like the applied science. I mean, this has something. Lots of things has something to do with national labs. We want to try to take advantage of this awesome like quantum physics, right? You can make good sensors for different things. And yes, for fundamental research or basic science, it would be nice. You can keep pushing the measurement precision, and maybe looking for new physics. But for like national labs or our sponsors, they care more about like, okay, I know this is awesome. Can you do this outside the lab environment, right? So you have to think about how I can bring this, make it like what we call like with more mature technology, and you can still take advantage and then do a sensitive detection for different things, right? So electric field is also kind of like that. The motivation of that is really want to see the state of electronics inside an enclosure, right? And especially we talk about a static charge. So like capacitor, right? And in order to see that, the direct signature is the electric field, and it has to be from DC to low frequency. The reason we don't need a true DC capability is because in order to see the electric field source, you have to map out the electric field distribution, and then you always have to move the sensor, right? And then they will allow to give us the electric field map, and then we can kind of figure out what the source looks like. It's kind of more or less like that MCG and MEG application for magnetic field. You try to localize your signal source at short distance. So in addition to that, we can do like proximity detection, remote activity. So it turns out electric field actually, it's a very good signal to see something happening at a far distance, because depending on the condition of atmosphere on the Earth or the configuration of the Earth's surface. And we can also see some tracing charge signature if something is made of plastic or dielectric material, and usually can carry static charges, and we can see that signatures. This can be used for extreme low frequency band to very low frequency band communication, and then again for geoscience, there are lots of electric field signal there, and bioscience, biology, humans or animals, other creatures, we always have some electric potential on the body, and that can be used for diagnostics. Okay, I think this is my last slide. Yeah. All right.
All right, so if there's any questions for Yuan Yu?
Yeah, I might ask some question not related. Have anything with GPS? Now the people try to figure out no satellite, try to figure out location. Is that possible in your technology?
Yes. So for example, are you talking about this one or others
No,
as
no,
well?
doesn't matter. GPS, right? We will try to avoid the satellite for
Yeah.
the global position system.
So there are a few proposals currently. You know, if you don't have GPS, right, and what you're going to do navigation or positioning, the direct approaches are you make a very good inertial sensors like accelerometer and gyro, but the problem is like they always give you the error after a certain amount of time because the error accumulates over time. So people also talk about using magnetic field mapping, you know, to locate your location, but it's kind of coarse positioning. It won't be as precise as GPS, but it still give you some idea. But on the other hand, usually they talk about like GPS jammed scenario. You still have some satellite signal, but not all of them. And then if you can have your own atomic clock with you, and that has something to do with the atomic clock part, you know, if you can make a really low power, small size atomic clock with good enough precision, you don't need a super awesome precision like today, you know, 10 to the minus 12 and 10 to the minus 13, back to 1950, that's the best in the world. And now it's a mediocre, you know. But that kind of mediocre performance is already good for GPS. If you lose, like say, 1 or 2 cells, I mean, usually you need 4, right? But if you only have 2, but you have also your local, then that can work. Yeah.
This was a wonderful talk. So have you been able to experimentally set up being able to move the E-field sensor in this way to do the work that you're talking about?
So I didn't talk about it because I can only talk about what I can talk. So yeah. Yeah, so but I can tell you the result I show you is already 5 years ago. And you know, in the past 5 years we are make it way much better, and we do have a handheld sensor and movable. Yeah, 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 sure.
Leave it to the Dean of Research to ask the NDA question.
So as far as the GPS, it's already mature that the cell phone towers work in place of a satellite. So you can get they call it assisted GPS, where cell phone towers work with the satellites to provide triangulation. My question is, can you get an atomic clock inside of here, inside the cell phone?
The one I just talked about, the active vapor cell clock, can be inside the cell phone. Yeah, it's about 1 centimeter long, and then like a 2-3 millimeter, you know, along the transverse dimension. Yeah, and it's consuming like 40 milliwatts.
Any other questions before we close out? All right, let's thank our speaker again.